And now, I was speaking about it is very hard if you get your results of your material 2 weeks after. And that's why we started a European research project, which was finalized in 2016, on the chemical and physical characterization of the excavated material, if possible, online. Normally, what is the normal situation in our field? We get these samples. The geologist takes the samples, makes it ready for the laboratory, goes into the laboratory. What do? Uniaxial, triaxial test, shear test. For the machine-driven tunnels, the abrasivity index, the LCPC, abrasivity indexes, breakability tests. At least in Europe, no chemistry. Infos which we get from that is then rock type, degree of degradation, RQD values, abrasivity, as I said. No information from the environmental impact. All of that born for do a static calculation. Now, when we started this project, we said, okay, let's take one of our tunnels which are right now under construction into consideration. We have Vienna, where Baden is standing in the middle. No, it doesn't work. This tunnel is 27 kilometers long, and we said where the focus of the center of these circles is it says 10 kilometers. There we have one of our portals of this tunnel. And the client said, yeah, but there is no industry. Why should we do that? There is no industry. And then we started the search for industries. I just brought one picture with me, quarries. I think a quarry could easily use the material coming out from this tunnel because it's amphibolites, it's granites, it's limestones. The points which you see around there is the quarries which are already existing. And the distance from the portal where the 10 kilometers is standing to the next quarry is not so far. But the problem is nobody gets in contact with the other. The quarry doesn't know something about the tunnel colleagues are not interested to get in contact in an early stage with this. But the answer from the client, there are no industries, and we did that for about 20 different industries, and there are many points around, is not right, because there are industries who are using mineral resources. And the question is, did we have tests for them available? What is it? The answer is no. Because we can tell the quarry our abrasivity index is this and that, which is out of interest for this industry. So our proposal is the following. Make your geotechnical properties as used, because we need them. We need the LCPC, we need the Los Angeles test, of course we need the point load, we need the uniaxial, the triaxial, we need the petrography, that's clear. But then it starts with X-ray diffraction, at least in the laboratory, first information of chemical consumption, and then we have to consider in which methodology will we build that tunnel. Will we bring chemicals into the excavation material or not? Will it be done by excavator, or how is it be built to get an idea what comes to the excavated material? And then a new field, geochemistry, intensively to be done in an early stage, that we know what are we expecting. And then the processing, which we spoke about. If we would like to bring it to the industry, what kind of processing would be needed? Then all of that global warming potential parameters. Everything in an early stage. We are in a preparation of a project. Then economy, of course. Is it economical to bring it here and there. Then the legal regulations, lots of them are available, and this brings us to a utilization. But we have to follow all of that, and this is what we didn't do in the past. For example, if we know we would like to produce this or that, we could check, or we could ask the machine manufacturer, if I'm talking about the TBM, for another spacing. The problem is the machine manufacturer for the moment are not so flexible that they say, okay, you can change your spacing. If you are in a hard granite, you get a spacing, let's say, of 65 millimeters, and if you are going to a weaker material, we can extend it. The machine manufacturer says, it's not possible. It's too hard to realize. There is one machine, by the way, by a very potential client, which is Kiruna, which is an iron ore mine, which has a TBM where they can change the distance, but the tunnel industry, I would say, is too weak to ask for that. Because if you ask for that, you get the answer, it's not possible. However, the grain size distribution is completely different, depending, of course, on the disk's distance. The chipping process, what we get, depends very much on this distance of the discs and gives then a material like that. We sometimes hear, yeah, but this material needs more cement because it's platy. Did you ever see, can you show me a publication where anybody comes with the result, the platy material needs more cement? We have concrete institutes. It was not be able to show that this material needs more cement. But it's well known, this material needs more cement, that's why it's not useful to reuse it for concrete. There was a development by the company of Wirth some years ago, a back cutting technology was not, I don't know, was not really used. I think the Uetliberg tunnel was once built by that in Switzerland. However, the grain size distribution of your result, what you get from the used technology, is very different. If you use a tunnel boring machine, you are in field number 1 with the result of the excavated material. So you get a lot of fine-grained material, which, this is the bad information, you cannot reuse because it's too fine-grained. If you would do this back cutting technology, what we see on this machine, you would get line number 2, much more interesting for the industry. If you do drill and blast, which is not possible everywhere, it's clear. If you do drill and blast, you get line number 3. It's you get much more blocks, and you can easily crush down the blocks if you think on the environmental. I just wanted to say this is the difference between TBM and drill and blast. From this point of view, environmentally reuse the material, the drill and blast wins the race, clearly. I mentioned the UCS is not really worth to be in a contract. In many contracts we see they fill in. If you are in this range of UCS, then you will get this penetration rate. We did tests together with the Colorado School of Mines, and the outcome was very clear. The UCS has nothing to do with the penetration. This was, by the way, then the reason why we started to develop this cutter force monitoring. And we developed a small test in the laboratory. So we take a sample which we always get from preparation of a project. So it's a cored sample, and the disc is a scaled disc, but with the same material of the disc what is then used on the machine, and with the same penetration in a scaled way than what you intend to go outside. And here we developed this disc cutter force management first. It was then installed on a real machine called core arm tunnel, a 33-kilometer long tunnel, to see if this can work. And we installed this technology on the on the left-hand side. You see a sketch of 3 positions of discs where we installed this cutter force management to see if it works. And it worked. What you see is some seconds of this disc cutter force management, and the outcome was very interesting. First of all, the load on a disc is completely different depending on the position where the disc is. You see the outer cutter has almost no load on it. The middle cutter has a very high load, and the inner cutter has a lower load. We always think that the TBM cutter head doesn't deform, but it seems it deforms. But this is a sidestep. The interesting information for us was, I mean, a 17-inch disc is normally developed for 270 kilonewton. What we see is we have 600 kilonewton and more. There are measurements, I think it is not in there, but there are measurements where we get 1,000 kilonewton on it. Clear, when the disc gets this dynamic load on it, we get very high loads on the disc. And then we did it in a way that you can directly follow in the cabin what are the forces along this disc, and when it's red, it's a high force, and when it's yellow, it's a small force. And we compared that with the geological documentation of the geologist, but didn't show him before. We just overlapped. So this is an information of the hardness of the material which is in front, which is one indicator for the industry or the concrete production. Can I use the material, yes or no? And how heterogeneous is the face in front? And then we developed another point, because coming from the NATM, we were used that face monitoring is essential. A geologist has to tell us what is the geology at the face. That's why we developed a camera system which is installed in the cutter head and makes photos of what is in front of the TBM. And this is just one ring what I show you here, but nowadays you can make a full picture out of it. So you can see the full face in front of the machine, because it's hard for the geologist to make an objective picture what is going on ahead of the machine. And therefore, we developed these cameras. There is a PhD running right now for 3D imaging so that you can really see what is the geology in front. Then we must know from the environmental point of view the pollution, and we measure, for example, the pH value. We have to measure all the values which are written in the law, of course. This is just one value. The question which we discussed then with the industry is, what are the parameters which we should know in the moment when we are doing the tunnel? And the outcome was, and how often do we have to do that? The industry replied, we would like to see the grain size, the grain shape, the water content, the elemental composition, the mineralogical composition, the amount of mica, and strength. Strength parameters which we said, okay, we fulfill more or less with the disc cutter load monitoring and the geological mapping automatically by the cameras. Then Hernknecht did a brilliant design and said, okay, it is possible to mount such a laboratory on the machine pretty close to the cutter head. Out of in this case it's a shield machine, out of the shield, because there's less space left. So we can put the laboratory, let's say, 1 diameter behind the shield. And if possible, we should run with the conveyor belt through the laboratory, or use a sampling unit, take it off there. And then after that, we crush it down and sort it into a material which can be used and a material which cannot be used. This was the idea when we started that. And in the laboratory, we should measure grain size, grain shape, chemistry, mass flow, water content. Some of them are already existing. Now, the group where we were working in had an elemental unit which was working with X-rays. And for that, he said the conveyor belt runs too quickly. The conveyor belt on a machine runs with 3 meters per second. This is too fast for the X-ray technology to detect it online. So because of that, we developed a system to take a hammer sampler, take off the material from this fast-running conveyor belt, determine the grain size and grain shape, send it through a crusher, and put it on a very slow-running bypass conveyor belt, make the water content, elemental composition, mineralogical composition on this bypass belt, and send the material back to the fast-running belt. Next question was, is it possible to install all of that in a tunnel, in a real tunnel, or is it too big? Again, Hernknecht did here the study on the Boslar tunnel, which is a German railway tunnel, which is right now under construction. And they came back with the information, yes, it's possible. If we need this, let's say, equipment for that, this would be possible to be mounted on a machine. Now, the X-ray has the hard fact that we get, again, legally, from the offices, no improvement to use that underground. Because, at least in Europe, X-rays are only allowed to be used in a room. Our room is moving. There is no law for a moving room. And that's why the authorities said a tunnel is a moving room. There's no law for moving rooms allowing X-rays. So we had to find another technology. However, there are some. I just mention here the possible technologies which we can use. Also the X-ray is here mentioned. But what you see is there is no technology which has only plus. The different columns say, okay, good or negative point. And there's no technology which has only good points. So it's not so clear which technology to be used. We built then a prototype in the factory of Hernknecht and did all of that what we had in the last sketch. I don't want to go too much detail in the prototypes. I show you a picture out of that then. The idea was we fill in the 3 boxes on the left-hand side, 3 different materials. We pour it on the conveyor belt, then send it through the crusher and then through the elemental unit, send the information from the elemental detection to the database. The database says this is material number A, B or C, and steers the conveyor belt to fill in the material into the right box on the right-hand side, A, B or C. And if it's working, this technology is working. This was the question. Just some pictures of the prototype which was built. These are the boxes where the 3 different materials were filled in. And the boxes were opened at different seconds. And then this is the detection unit. And at the end, you cannot see that, there are 3 boxes and the conveyor belt can be shifted left-hand side, right-hand side to fill in the right material in the right box. Then one major development, or not development, just looking in the industry, was we are doing sieving analysis. Stupid job, huh? You get the material, do sieving analysis with the students or whoever does it, and gets a sieving grain size distribution. But there are, in the industry, technologies available, fully automated. So you put cameras to the conveyor belt, 4 cameras, and you see the different grain size distributions. The blue line is the one which we did in the laboratory with the sieving meshes. And the others are the fully automated ones, and you see they are laying one over the other. So sieving analysis, I would say, can really be automized, and you get the result what is on the conveyor belt in the second when it's running on the conveyor belt. Mica detection, we developed an own apparatus for that. Due to the time I go over that, just some photos from these detection units. What you get from the elemental composition is a clear what is in. You have to, let's say, learn the system in the laboratory first, but then you get it online, what is on the conveyor belt. And this is, from our point of view, very useful. Database system, I go over that, because I want to come to a point, where are we now? We are setting up a research center now, which I will speak tomorrow morning in an own presentation. We are building about 3-kilometer research tunnels, full scale, where we will test this prototype on site. So next year, in spring, we will be ready. For the moment, we are doing the design drawings for this prototype, which will be used in the full-scale research tunnels to show if it works. I will speak about that tomorrow morning, so I go over that. And what we found is a technology where we get an approval from the authorities, which is a laser-induced breakdown spectroscopy. A nice methodology where I would like to show you a short film of, where we make 350 measurements in 1 second, and we do 20,000 measurement points in a second. So we produce a plasma out of the material, and the plasma brings back the atomic reactions to the detector, and I would like to show you a short film about that, how it works in the laboratory. And in the second, when the plasma is detected, you know what is lying on your conveyor belt. And I would ask the jury, can you start the film which we tried in the morning? We cannot see the full picture. Yeah, that's good. What you see on this film, please start it then again. If it stops, start it again. What you see is, what you hear is the laser which produces a plasma. This plasma is, I mean, you shouldn't bring your finger in, is about producing 20,000 degrees. And because of this, it detects the atomic reactions which are detected by there's a hole in the laboratory box, you see that? There's the detector in. And on the left-hand side, there's a computer where you can, in the moment where you send your high temperature, where you produce your plasma, you can see what is on the conveyor belt. And now the next film, please. Here we are running the laboratory test with the 3 meters per second to see if the technology still is working then. And you see when the material goes under the plasma stream, it makes a flash. And every time when you have that, you get immediately on your screen the result, what is the chemical consumption. And this is the technology which we got approved from the authorities. If we are able, let's say, to make a fence around it, but this is possible, is now the latest state-of-the-art of online detection of what is the excavation material consisting of. Thanks, we can stop that. And brings me really to the last slide. We produced now tubing elements out of tunnel excavation material. This is our test facility for tubing elements. And we can say the results of these tubings produced of tunnel excavation material are even better than those produced with fresh gravel. And this shows that it is possible to do a reuse to be environmentally friendly. This was my last slide. I took 5 minutes more. Thanks for listening, and I'm happy for your questions.